All right, engineering students, welcome. Today, we are going to pull back the curtain and demystify the timing parameters that are basically the hidden heartbeat of every single digital device you own. So let's jump right in.
So let's kick things off with a pretty fundamental question. When a signal travels from one part of a circuit to another, does it just, poof, get there instantly? The way we draw it in our intro classes, you'd probably think so. But you know reality. It's always a little more complicated.
You've seen this a million times, right? In our textbooks, on the whiteboard, we draw these perfect, clean square waves you see on the left, instant jumps from low to high. But in the real world, well, it's a lot more like the signal on the right. Kind of messy, sloped. They take time to rise, they take time to fall, and they definitely take time to travel.
So where do all these delays come from? Let's break it down, and we'll start with the signal's journey along the wire itself.
Okay, so the first and honestly the most fundamental delay is just the time it takes for an electrical signal to physically move down a wire. We call this, pretty logically, wire delay. You'll also hear it called transport delay. It's a hard limit set by physics,
and this shows it perfectly. Look at the input signal, x prime. It goes high, right? But notice the output, y, doesn't react instantly. There's this little gap, this tangible delay that's marked as delta before y even sees that change. That right there is wire delay in action.
Okay, that makes sense for one wire, point A to point B. But what about something like a master clock signal? You know, a signal that has to be sent out to a bunch of different components, and it's critical that it arrives at the exact same time to keep everything perfectly in sync.
Well, here's the kicker. In reality, it almost never arrives at the exact same time. The paths have different lengths, different electrical properties, and that means the signal shows up at slightly different moments. This timing difference is a supercritical concept we call skew.
And wow, this illustration just nails the problem. The clock signal gets sent out, but because the wire delays T1 and T2 are different, it reaches the two flip-flops at different times. The timing diagram on the right shows you the result. The clock edges are out of sync. That's skew, and let me tell you, it can cause huge problems in a synchronous circuit.
So, we get the delays that happen between the components, but what happens inside the components themselves? Now we're going to zoom in and go inside the logic gate to see how it actually processes a signal.
So a logic gate, it's not magic, right? It's a physical circuit, and it takes time to react. The time from an input changing to the corresponding output changing is what we call the propagation delay. This is basically the single most important measure of how fast a gate is.
Now you might wonder, how do we measure this consistently? Well, the standard way is to measure from the midpoint, the 50% point, of the inputs transition to the midpoint of the outputs transition. This just gives us a really consistent reference point for both rising and falling signals.
And here's something that trips people up sometimes, so it's really important to get this. A gate can have two different propagation delays. The time it takes for the output to go from low to high, which we call TPLH, isn't always the same as the time it takes to go from high to low, or TPHL. It all comes down to the underlying physics of the transistors. One switch can just be faster than the other.
Beyond just the delay, we also really care about the shape of that signal. Like how fast does it actually change? We define this with a few terms. First is rise time. That's the duration of the low to high transition. Then we have fall time for the high to low transition, and we also measure saturation time, which is simply how long the signal stays stable at its high or low value.
All right, that's enough theory for now. Let's put this into practice and solve a little puzzle. For our first challenge, we are going to take a signal graph and find all of these timing parameters ourselves. Let's do it.
Okay, so here's our setup. We have our input signal, V, and our output, VO. All the key points in the transitions are marked with a time value in TU, or time units. Our job is to use these points to find all the delays and times we just talked about.
Okay, let's walk through this together step by step. First up, the rise time for the output signal. That's how long it takes to go from low to high. So we calculate that as T7 minus T6. That gives us 2 time units. Easy enough. Next, the output's fall time. That's the high to low edge. So we calculate it as T3 minus T1, which is 4 time units. Then saturation time, how long it stays high. That's T4 minus T3, or 6 time units. Okay, now for the trickier ones, the propagation delays. Let's start with TPHL, when the output goes high to low. We need the midpoint of the output's falling edge, which is between T1 and T3, and we subtract the midpoint of the input's transition that caused it, between T0 and T2. That difference is our TPHL, 2 time units. Finally, TPLH, when the output goes low to high. We take the midpoint of the output's rising edge between T6 and T7 and subtract the midpoint of the input's causal edge between T4 and T3. That gives us 5 time units. See? Not so bad when you break it down.
Great work on that one. Now for a different kind of puzzle. Instead of finding the delays, what if we're given the delays and we have to find the time points on the graph? Let's try working backwards.
So this time, they're handing us the rise time, fall time, saturation time, and both propagation delays, all in microseconds. We also have a few known time points, like T0, T2, and T5. Our mission is to solve for all the missing time markers on the graph.
We can just chip away at this piece by piece like a logic puzzle. For example, we know the rise time is 4 microseconds, right? And we know rise time equals T3 minus T2. Well, they gave us T2 as 6 microseconds, so we just solve for T3, and it's got to be 10 microseconds. It's just simple algebra. Okay, next, we know saturation time is 7 microseconds, and that equals T4 minus the T3 we just found. So T4 is 17 microseconds. You see the pattern? We use each known value to unlock the next unknown. It's like a domino effect, working your way through the puzzle until you've solved the whole thing.
So, we've done the math, we've dissected the graphs, but let's just take a step back and ask the big question. Why do engineers obsess over these tiny nanosecond-level delays? Why does any of this actually matter so much?
Because these delays, they're not just numbers on a page. They are the ultimate speed limit of our digital world. The total propagation delay through a circuit is what dictates the absolute maximum clock speed a processor can run at. Understanding skew and delay is what prevents catastrophic data corruption from signals arriving at the wrong time. This isn't just some academic exercise, it determines the fundamental performance limits of everything, from the phone in your pocket to a massive supercomputer.
And that leaves us with a final thought to chew on. As we keep pushing technology, making chips smaller and faster, these delays get even more critical and way harder to manage. The challenge for the next generation of engineers, for you, is this constant battle against the fundamental limits of physics. So the question is, how will we continue to win?